Minasan yokoso. Welcome to the Morikami Museum and Japanese Gardens. I'm so glad to have you all here today. And today is a special day. It is Tanabata. Tanabata is written with the characters for 7 and evening. So Tanabata, 7th evening of the 7th month. So 7/7. But throughout Japan in different regions, it is celebrated at different times of year, a little bit later in July or early August. But it is a very exciting festival. And it's also called the Star Festival, which is part of why we're here today. We're hoping to get Dr. Ada online here with us. He is an astrophysicist at Florida Atlantic University. And he is going to explain for us a little bit more about the stars and the universe that we live in. And for any of you who have already been here, we do have an exhibit up right now called Painting Enlightenment. Beautiful exhibit. If you haven't seen it, I highly recommend you go through the gallery today after the lecture. We're open till 5. And Painting Enlightenment is approximately 40 paintings, all by one artist, Mr. Iwasaki Tsuneo. And he was born in 1917. He lived through the war years. Then he became a biologist for many years. He actually was a virologist, studying viruses of all things. And later on, after he retired, he decided to devote himself to the Buddhist practice of shakyado. Shakyado is copying out sutras or Buddhist texts. And it's just a way of, focusing your mind on something really positive. It's a good habit to have. So what he did is he took this tradition of copying out the texts and he added something very new and very different. He put the text into his compositions. So he takes the Chinese characters and pretty much weaves them into compositions of various types of cat's eye or lightning, some lovely mother ducklings, also some more familiar Buddhist figures. So it's a really beautiful exhibit and we've been getting some nice feedback, so I hope you get to see that today. And let's check in with our good doctor. Here we are. There we are. Hello. There we are. Hello. Welcome, Dr. Ada. So glad you could be with us today at long last. Here we go. And without much ado, I've been doing the little intro already, so I'm going to go ahead and let you take over. I'll just do a brief introduction. Dr. Ada Sarajedini is at Florida Atlantic University astrophysicist, as I mentioned. He got his PhD from Yale in 1992 and has written over 500 publications. So we're really lucky to have him here today to help us better understand these beautiful paintings. So take it away, Dr. Ada.
Okay, can you hear me okay, everyone? All right, so let me go ahead and share my screen here. All right. So I'm going to go ahead and start the slideshow. Thank you very much for having me today. And I was asked to speak about this painting, The Big Bang and E = MC squared. And so when I started to research it and learn about it, I realized this is a very complicated painting. There's a lot going on here. There's a lot to talk about. And I wasn't sure whether I could fit it all into 45 or 50 minutes of a presentation. I'm going to do my best. I really want to give you a flavor for what the artist has included in this amazing work of art. So let's start going and talking about it. Before I do that, I want to just plug my podcast. I do a occasional podcast called Astronomy Minute, and it's on Spotify and Apple Podcasts, and it's just a whole bunch of different topics about astronomy if you're interested in hearing short descriptions of the different topics. It's called Astronomy Minute because every podcast is only 1 or 2 minutes long. So it's very short, each one, and the website is down there at the bottom. The website organizes the 150 some episodes into topical areas. Excuse me for a minute. I've forgotten to mute my phone. Okay, so let's talk about this. So this is actually a quote from the brochure that describes the painting. And it goes like this: form is emptiness, emptiness is form. After completing this painting, Iwasaki reflected, "The karmic tie that binds all beings brings about the cycle of life and death. I too am bound by this recurrence of the life cycle. The occurrence of the Big Bang gave rise to my being. For this, I simply bow to the universe." Through this masterpiece, Iwasaki enraptures viewers to behold the boundlessness of the universe and experience our interrelatedness, thereby healing the delusion of separateness that causes so much loneliness and despair. So that is, in a nutshell, what the painting is designed to convey. And down here in the red, I've kind of translated that into science speak. And all that says the following: the painting illustrates the interrelatedness of every entity in the universe by connecting the Big Bang, the event that created the universe, with E equals mc squared, the equation which describes how the atoms and molecules that make up galaxies, stars, planets, gas, dust, and our bodies were produced after the Big Bang. I want to take the rest of the talk then and give you more detail about that red text right there. Now, if you go out at night and look up in the sky at a dark site, this is what you see in the sky. This is the Milky Way galaxy as viewed in the sky from a dark site. And if you take the entire image of the sky and look at the galaxy, this is what you find. So on the right here, it's a 360-degree photo of the sky showing you what the galaxy looks like as it extends from horizon to horizon. What you see here is, this is a cartoon showing where we are in the galaxy. The Milky Way is a disk, essentially a flat plane. We're about 2/3 of the way out from the center. And when we look perpendicular to the plane, we see very few stars. That's what you see up here and down here in this picture. When we look along the plane, we see a thick band of many stars. And that's what you see here along this, in the middle of this picture. This is along the plane view, and above and below are the above and below the plane view of the Milky Way. Almost every single star and object you see in the sky at night belongs to our galaxy. And I'll talk more about that as we go along. Now, what I've done here is taken Iwasaki's painting, which is at the top, and compared it to what the Milky Way galaxy looks like as viewed in the sky at night from a very dark site. And what you see, of course, is a lot of correlation, a lot of relatedness between this picture at the bottom, which is the Milky Way, and the painting by Iwasaki called The Big Bang equals mc squared. What I want to do is go through and describe some of the things in here. Before I go any further, since I can't really see any of the people in the audience, Carla, are we doing questions at the end, or can people ask questions in the middle?
We'll do questions at the end. Okay.
Okay. All right. Good. So be sure to keep your questions, in mind, and ask me at the end, please, because I want to be sure as much of this that I'm saying is clear and as understandable as possible. So this is the comparison now of the painting, excuse me, with the actual photograph of the Milky Way in the sky. Now let's dissect the painting and look at it in more detail. First, though, I want to talk a little bit about the speed of light. The universe is a time machine. The speed of light is finite. So when you turn on a flashlight and you see the light beam go across the room and hit the wall, that doesn't mean that the light does that instantaneously. It actually takes some time for it to travel across the room to hit the wall. And the speed of light is 186,000 miles per second. It's so fast, it seems to be instantaneous, but it's really not. So for example, the moon. Light from the moon comes to us and is 1.5 seconds old. We see it as it was 1.5 seconds ago. Excuse me for 1 second. I got to take care of one thing, please. All right. Sorry about that. I had to take care of one thing that the that fire drill left hanging, let's say. So the sun is 8 1/3 minutes away. The light we see from the sun left it 8.3 minutes ago. And so when we look out in the universe, we see things as they were in the past. We never are able to see the universe as it is today. And that's actually a good thing. We can use it to our advantage. We can look out into space, look back in time, and see how the universe was in the past. So for reference, 1 light year, the distance light travels in a year, is 6 trillion miles, or about 9.5 trillion kilometers. When we look out into space, we're looking back in time. So keep that in mind as we go along in the presentation. So when you go out at night, look up in the sky, you're looking back in time. Now I want to start now by giving you a sense of our place in the galaxy and of course in the universe. The next few animations are going to give you a sense of the scale of the galaxy and where we are relative to it. And so this first slide shows you the sun in the middle and about a dozen or half, well, maybe a dozen, 2 dozen nearby stars. And this bar up here is 10 light years. So this is the distance light travels in 10 years right here is this bar. So many of these stars that are near us are within 10 or 20 or so light years from us. So the nearest star, Alpha Centauri, which is here, it's about 4 light years away. Okay, and we're going to zoom out here for the next step. Now we're out to the scale of hundreds of light years. That's what this bar is here. So the sun's in the middle, and these are all stars near the sun that are within a few hundred light years of the sun. One more step, and we start to see the spiral arms of the Milky Way galaxy. And these are what are shown, what are drawn here as these lighter regions. The sun is still in the middle, but you now begin to see other features in the neighborhood of the sun that are in the Milky Way galaxy. And then finally, this is the Milky Way itself. Now we're inside the Milky Way. We can't photograph it. So every rendition you see of the Milky Way galaxy is an artist's conception. But it's based on real data, that we think that's the way the galaxy would look if viewed from the outside. And now we're on the scale of tens of thousands of light years, as this bar up here shows. So the sun is about 2/3 of the way out right here, and this is the way the galaxy looks. Let me just quickly go back real quick. Here we are, the solar neighborhood, tens of light years. Here's the galaxy, 10 or 20 or 50,000 light years. That's how large the Milky Way is. Remember that a light year is the distance light travels in a year, which is about 6 trillion miles. And this one slide encapsulates all those previous slides into one slide. So here we're at the Earth, we're in the solar system, the Milky Way galaxy. The Milky Way is part of what's called the local group of galaxies, which is right here. And the local group is part of the local supercluster. Now, I'm presenting all of this to put that painting in perspective, so you really get a full viewing and understanding of all the things that Iwasaki's painting encapsulates. And that's why I said earlier that this was a tough presentation to write, to try to explain all those things in that painting. Now, I want to talk a little about the universe itself. I'm not going to go into much detail, but we have a lot of pieces of evidence and observations that indicate the universe had a beginning, and that beginning is called the Big Bang. And these are 2 graphical representations of what happened after the Big Bang. So on the top, the left over here is, the Big Bang over here on the left. The universe expanded very fast. It was very dense at first, very hot, expanded, and over time created stars, galaxies. Those evolved over time, and on the right is where we are today. The universe is 13.8 billion years old. I'll just say 14 for convenience sake. The lower graphic shows the same thing in a bit of a different form. On the left is the Big Bang, the explosion that began the universe. And as we go to the right, we form the first stars, the first galaxies. They evolve, they produce the heavy elements. I'll talk about that in a minute. and then on the right is the present day. So again, the universe is about 13.8 billion years old. And the Big Bang is the event we believe created the universe itself. Now I'm going to go and talk about some of the aspects of this painting. And I realize there's a lot here, but I think it's important to, get a sense of the immensity of this painting and what Iwasaki, the message Iwasaki is trying to get out to the viewer. These are the different kind of objects that are illustrated in this painting. Let's talk about each one in turn. Now, as I said, we live in the Milky Way galaxy. This is an artist's conception of it, of course. Here we are at the sun, about 2/3 of the way out. The galaxy itself is 100,000 light years across. And we're about, as I said, about 25,000, 26,000 light years out. And it takes us about 250 million years to go around the galaxy once. So we're orbiting the center of the galaxy, and we go around 4 times every billion years. Viewed edge on, the Milky Way would look like this. These objects here, these little fuzzy things that are above and below the plane, are called globular clusters. And this is a close-up of one of them. Here it is. This is the actual picture of the globular cluster. On the left is Iwasaki's representation of it. Why did he include these objects? Because they're thought to be the oldest objects in the Milky Way galaxy. They're thought to have been formed soon after the Big Bang. The universe is 14 billion years old. These objects were formed about 1 to 2, maybe 3 billion years after that. So they are the oldest objects we know of in our own galaxy, and they're called globular clusters. Another object depicted in the painting is the Andromeda galaxy. This is the depiction of the painting at the top, and the bottom is the actual photograph of this galaxy in the sky. Andromeda looks about the same as our own galaxy would if we could view it from the outside. It's 2.5 million light years away. So the light we see from it left it 2.5 million years ago, well before our species existed on this earth. The light you see from it today left it 2.5 million years ago. Now, Iwasaki also depicts clusters of galaxies. This portion of the painting on the left are those. And what I have shown in the middle is the nearest major cluster of galaxies to us. It's called the Virgo cluster. It's 50 million light years away, and it contains almost 2,000 galaxies. This is the picture of the whole cluster, and I've just kind of extracted individual galaxies from this photo to show you what some of these galaxies look like close up. Another object in the painting is called the North American Nebula. As it turns out, this nebula looks like the continent of North America. And what I show here is the depiction of the painting. And in the upper part, you see, this is the constellation of Cygnus in the sky. And it's hard to see, but there are lines connecting the major stars that make up the constellation. And over here in this portion of the constellation is this nebula, which I zoom in on it here in the lower part of the slide. And it looks like North America. So we have Florida is here. Mexico and the Central America is here. New York City is somewhere up here. And Seattle is over here on the left. So a nebula, in this case, is simply an area of space that's filled with gas and dust that's just floating there. And I'll tell you in a bit where it came from, but it's floating in space, and it's illuminated by nearby stars. The gas and dust normally, when it's just floating in space, is dark. But if it's close to stars, the stars can light up the gas and make it shine with its own light. And that's what we see here, the North American Nebula. Now, another depiction in the painting is called the Pillars of Creation, and this is what it looks like in the Big Bang painting itself. And this is actually a depiction of what's called the Eagle Nebula. So this is the Eagle Nebula here. This is a photograph of it from the ground. And what I've done is zoomed in to this portion here in the rectangle, which many of you have probably seen before. And this is what it looks like from the Hubble Space Telescope. So this central picture is the Eagle Nebula from the Hubble Space Telescope. And then further zooming into this kind of first pillar over here to the top of it, it looks like this. And you'll see a lot of detail in this part of the nebula with pillars and filaments and things sticking out in every direction. And as I said, nebula usually are gas and dust. In this case, this is dominated, the dark areas are dominated by dust. Now, what is dust? Well, in astronomical parlance, dust is basically complex molecules, things like carbon monoxide, molecular hydrogen, carbon dioxide, various molecules that are floating in space. And these molecules are the raw materials for making stars and planets, as I'll talk about in a minute. And so if you zoom in on these, zoom in on these filaments up here, you see something like this. This is a montage of what are called protostellar disks. Each of these boxes represents one or multiple stars in the process of forming. And you can see most of them anyway are not just spherical, they're flattened or irregular in shape. And the reason for that, I'll show you why that is in a minute, has to do with the fact that these are actually planetary and stellar systems in the process of forming. So just going back to this, it's called the pillars of creation because there are stars forming inside these pillars. And whenever stars form, you almost always have planets forming around them as well. And this slide here shows you the process of star and planet formation. So starting at the top, you have an area of a volume of space with gas and dust. Within that volume, higher density areas form. Those higher density areas cause this larger gas cloud to collapse, start to rotate, and it collapses into a disk. And the central part of it gets very hot. Well, I should say it gets hot. The outer parts are cooler. And the very center, if it gets hot enough, then can form a star. And so it heats up, it flattens out, it rotates faster. And what you have left here is basically a protoplanetary, protostellar disk of material that the outer parts form planets and the inner part forms a star. And I have also included little photographs of actual protoplanetary disks that are observed in these areas of star formation. What's important to realize is that the center will only form a star if the temperature is high enough for nuclear fusion to occur. I'll come back to that in a few slides, but that's what determines what a star is. If the center is hot enough for fusion to occur, and fusion is a form of energy. So when a star is formed, it ends up, or it starts its life on what's called the main sequence. This diagram is one of the most important diagrams in astronomy. And what it shows is it plots temperature on the horizontal axis, luminosity or brightness on the vertical axis. And these are all the different types of stars that we observe in the sky. So the hottest stars are over here on the left, and the brightest, of course, on the upper left. The coolest stars are over here on the right, and the lower right are the faintest, coolest stars. And then the giants and supergiants are in the upper right. So most stars begin their lives on the main sequence. This is where the sun is right now, right there. And when they first form, they start on the main sequence. And that's where they begin their process of fusion, producing energy through the thermonuclear fusion reactions. And as they evolve from the main sequence, and these arrows show the general direction of evolution, as they evolve from the main sequence to the giant branch or giant region, they produce heavier and heavier elements inside them. Okay, how does that work? Well, this slide, I know it's a busy one, but it encapsulates the process by which the universe makes us. The process by which the universe makes the elements in the periodic table that form our bodies and everything we see around us. So on the left, the Big Bang, when the universe was first created, it was almost all hydrogen and helium. Very simple elements. Well, obviously, there's more to the Earth than hydrogen and helium. There's carbon, nitrogen, oxygen, aluminum, mercury, gold, silver. Where did that come from? Where did all those elements come from? Well, the simple answer is they were produced in stars. And as the universe evolved from the left to the right, it became more and more enriched in what are called heavy elements or metals. And those are produced in stars. And they're distributed into the interstellar medium to make more stars through these mechanisms down here, which I illustrate. And I'll come back and talk about these later. But the bottom line is that the heavy elements that make up most of the universe were made in stars. And that's where this equation E equals mc squared comes from. And I want to talk about that a little bit in the next few slides. So this is the periodic table, which I'm sure many of you have seen in a high school chemistry class, right, on the board. And what I want to point out is that hydrogen and helium are at the top. They're the simplest elements. Everything else, and they came from the Big Bang. And everything else we call metals in astronomy came from stars. Now, most astronomers call these metals. Obviously, there are astronomers who study the individual behavior, of individual elements. But overall, astrophysicists call everything heavier than helium a metal because to one degree or another, those elements were produced in stars. All right, now where does E equals mc squared come in? Well, generally speaking, the simplest reaction in fusion is inside stars is to take 4 hydrogen atoms, fuse them together, and make 1 helium atom. This process of nuclear fusion produces energy. And the question is, how? But the bottom line is this energy production mechanism is what makes stars shine. That's how the sun is shining right now. In the very center of the sun, this reaction is happening. And in fusing 4 hydrogens to make 1 helium, the sun makes energy. How? Well, here it is. I'm sorry about all the numbers here. I just want to really just illustrate the important point here, which is this equation, E equals mc squared, is Einstein's brilliant deduction about how energy and matter are related. Energy is the E, matter or mass is the m, c is the speed of light squared. So when I convert 4 hydrogens to 1 helium, the mass of 4 hydrogens is given by this number. The mass of 1 helium is given by this number. They're not the same, right? The mass of 4 hydrogens is slightly more than the mass of 1 helium, very slightly more. A mass difference of 0.7%. That mass difference, that lost mass, if you will, is what's converted to energy to power the sun. So that small amount of mass difference, this difference of 0.7%, is put in this equation for m, and that's how you calculate E. But remember, c is a very large number, the speed of light, 186,000 miles per second, and you're squaring that. So c squared is a very, very large number. And so you take a very large number, and even if you multiply it by a small number, which is 0.7% in this case, the energy output is huge. And even given that, the sun has enough mass to fuel its current energy output for another 5 billion years. The sun and the solar system have already lived about 5 billion years. They have another 5 more to go. And at that point, after 5 billion more years, all the hydrogen in the center of the center of the sun, where the fusion is going on, is going to be used up. And of course, the sun will then evolve to another phase in its evolution. But this is the significance of this equation, E equals mc squared. It tells us how to equivocate mass and energy. And this is what basically fuels the energy output of stars. Now, over time, stars evolve. They fuse hydrogen to helium, helium to carbon, carbon to neon, et cetera, to heavier and heavier elements. And so over time, at the end of a star's life, especially the more massive stars, this is what the interior of the star looks like. The surface is made of hydrogen. The next inner shell is helium, then carbon, neon, oxygen, silicon, and then the very center is made of iron. This is called the onion skin model for the evolution of a star. And this entire onion skin structure is governed by this equation, E equals mc squared. So what started in the universe as just hydrogen and helium is then fused and converted to all these other elements as stars evolve and distribute their elements to the interstellar medium, which is then used to make new stars, which have more metals than the previous generation. And over time, over multiple generations of stars, you generate and produce the elements in the periodic table. So just showing you this again, as I said, stars begin their lives on the main sequence, converting hydrogen to helium, and over time they evolve off of the main sequence when they've used up all their hydrogen, become giants, and successively produce heavier and heavier elements, as shown in this onion skin model of the end state of a star. And this is what we're kind of left with. This is the periodic table showing you where different elements came from. So hydrogen and helium, as you can see, they're from the Big Bang, and then everything else, all the other elements, come from different combinations of stellar evolution. So things like low mass stars will produce the ones with the blue. Exploding white dwarfs will produce the ones with the orange. Different nuclear processes, nuclear decay, cosmic ray spallation, etc., will produce the other elements, and including massive stars that explode and neutron stars that explode. I don't have an explanation for each of these items. I can describe them for you in the Q&A, but that would be somewhat of a whole other talk to talk about all these processes in detail. But the bottom line is that all the elements in the periodic table are in one way or another originating in stars through this process governed by this equation, E equals mc squared. Now I'm going to move on now to the sort of the central part of the painting, which is the black hole at the center of the Milky Way, and that's what this part of the painting represents. And talk a little bit about what exactly this is and its significance. First, though, what is a black hole? That's a good question. What is a black hole? Well, it's really simple. In its most simplest terms, a black hole is an object whose escape velocity is so high that not even light can escape from it. So here I show the Earth and a cannon, essentially shooting a cannonball in a certain direction. If you shoot the ball with a certain amount of velocity, it'll go up and come down. If you shoot it faster, it'll go further, but it'll still come down. Then there's this velocity that you can shoot it at where it'll go into orbit around the Earth and will come right back. Then there's an even higher velocity called the escape velocity. If you shoot this cannonball at the escape velocity, it will escape the Earth's gravitational pull and, be beyond the Earth's influence and be able to travel somewhere else, to the moon or wherever. That velocity is called the escape velocity of the Earth. And for the Earth, it's about 25,000 miles per hour. This is how fast rockets have to go to leave the Earth's gravitational pull and, go to the moon or wherever. Well, for the sun, that number is 1.4 million miles per hour. It's greater, obviously, because the sun is more massive. It has more gravity associated with it. And so you'll need to travel faster to leave the sun's gravitational pull. So imagine an object whose mass, and by the way, escape velocity depends on the mass and the radius of the object. So imagine an object that's so massive, the mass is high, and so small, the radius is low, that the escape velocity equals the speed of light or exceeds the speed of light. that object is called a black hole. So that object whose escape velocity exceeds 186,000 miles per second cannot be seen because no light can escape from it. That's why it's called a black hole. Now, it's important to keep in mind that black holes are not, in some ways they're depicted as cosmic vacuum cleaners going around the universe, just sucking everything up. That is not the case at all. As a matter of fact, if you were to take the sun, the mass of the sun, replace it with a black hole of the same mass, what would happen to the Earth? Now, if we were there in person, I'd call on you, you could raise your hand, but I'm assuming you're all pondering this question. If you replace the sun with a black hole of the same mass, what would happen to the Earth's orbit around the sun? The answer is nothing. Nothing. The Earth would be cold and dark, but would still be moving around the sun at the same velocity, in the same motion and the same orbit. Black holes are just simply intense sources of gravitational attraction and a gravitational force. That's a black hole. Now, what does it have to do with the painting? Okay, so in the center of the Milky Way galaxy, there's a black hole, a supermassive black hole. Now, if we look in the sky, we can actually look in the constellation of Sagittarius and see the center of the Milky Way. Here's a picture of the sky. This circle shows you the center of the galaxy, but you can't see much with your naked eye. Why? Not because of the black hole being black, it's because there's a lot of dust between us and the center of the galaxy. So you can't see because the light is obscured by the dust itself. Okay, but we can look at the center of the galaxy in other kinds of light, not just light your eye can see, but longer wavelength light, like infrared light and radio waves. When we do that, this is what we see. So on the left, and this is now 250 light years across, these images are of the center of the galaxy in radio light. Radio waves are very long wavelength light that travels to us from the center of the galaxy. And because they don't have color intrinsically, we add color based on how intense the radio waves are from those parts of the center of the galaxy. And so this box, we can zoom in on it, and there's the center even closer up. We can zoom in on that box even more, and this is what the galaxy center looks like in infrared light. Each of these dots is a star at the very center of the galaxy. And we can observe these stars over many, many years and watch them move, watch them orbit the supermassive black hole at the very center of the galaxy. And here's what it looks like. These dots now are individual stars orbiting the very center, which is indicated by this sort of five-pointed star. And these are observations taken at the Keck telescope in Hawaii. And these observations actually won Andrea Ghez the Nobel Prize in physics a couple of years ago for discovering the massive black hole in the center of the Milky Way. So this is 1995, and I'm going to run this movie forward and show you how these stars move. These stars are orbiting the center of the Milky Way around the supermassive black hole at the very center. Okay, so that was 1995. This is 2016, so about 10 years. And you can see the orbits that these stars followed during that time period. Let's just show it again. And the amazing thing is that these stars are orbiting the center of the Milky Way based on the influence of this black hole at the very center. Well, we can use the motion of these stars and calculate the mass that black hole has to have to cause these stars to move, as they do over this decades-long observation. Well, the mass of that black hole is in the millions of solar masses, 2 to 3 million times the mass of the sun. So in this little, volume of space in the center of the galaxy, there's something there that we cannot see, but that is the equivalent of millions of times the mass of the sun. And the conclusion, therefore, is that it's a black hole because it's very massive, but not giving off any light. And it's confined to a very small volume. So there's very good evidence that the center of the Milky Way galaxy has a supermassive black hole in it. And the question then is, well, all right, so the Milky Way has one. What about other galaxies? Is this unusual? Is it unusual for our galaxy, the Milky Way, to have this very massive black hole in its very center? And you can imagine what the answer is. The answer is no, it's not unusual at all. It's actually very common. And so this is a galaxy in the Virgo cluster called M87. Virgo cluster, as I showed you earlier, this is a picture of it. M87 is right in the middle, just about. You can zoom in on it, and this is M87 itself. And last year, 2019, I guess, the first photographs of the massive black hole in the center of M87 were taken. This is what they look like. So here again is M87. There's the galaxy itself at the very center. We zoom in on it at the very center of the galaxy, and this is what the black hole looks like at in the very core of galaxy M87 in the Virgo cluster. This central part is the actual black hole, the very, the interior. All this stuff, this light outside, is material that's falling into the black hole and giving off light of its own. So, the most minuscule, dot in the very center of this picture is the black hole. All this other stuff is material falling into it and giving off its own light. And these observations were taken by what's called the Event Horizon Telescope, which is actually a network of telescopes around the world that observe in the radio part of the spectrum, as I said earlier, the radio waves, to get a very high resolution photograph of this black hole. All right, so getting back to the painting, we've covered quite a bit of information here on this painting, from the Big Bang to the E equals MC squared, to how that encapsulates the production of stars, galaxies, planets, gas, and dust, and how all that material is interrelated because it was produced in the Big Bang and the elements were enhanced and synthesized inside stars. And the equation E equals MC squared is what governs how that synthesis essentially happened. Okay, this is my last slide. I'm going to leave you with this. This is my podcast again. I want to thank you for your time, and I'll take any questions you might have at this time. Thank you very much.
Hello. Okay, thank you. That was terrific. Thank you so much. I really got a lot out of that, and I'll start off with a comment just saying, Iwasaki's work is really deep, and it really helps to look at it over and over. And I think, especially after hearing about the black hole and how emptiness is at the heart of everything, that I just find that so fascinating. Thank you so much. If anyone would like to come up and ask a question on screen, I just invite you to come to the microphone so we can get you on camera as well.
Hello, sir. Thank you very much for your time. It was very informative. Does a star create the planets that orbit the star? Does the sun that we have, does it create Mercury, Earth, and all the planets that orbit it?
I think what you're asking is, are stars the ones responsible for the creation of planets, right?
Right. And then I'm getting to how does the metals from a star, the star creates the metals, how do those metals get to the planets? I mean, Earth, we have the metals in the Earth, right?
Right. So the short answer to your question is that no, the stars are not responsible for the production of the planets, but the star does influence what the structure of the planets themselves. So the elements that make up the star and the planets come from the original, this kind of big cloud of gas and dust that was present at the beginning of the formation process. So whatever elements the star and planet are going to have are in this original gas and dust cloud. Now, over time, this gas and dust cloud collapses, rotates, flattens out, and the very center becomes a star, and the outer parts are where planets could form. So the elements, for example, that are in the sun are largely the same as those that are in, say, Jupiter and Saturn. But the only difference is that the sun is obviously a lot hotter than Jupiter and Saturn. So different elements are going to be more prominent, say, in the sun than they are, say, in the Earth or Jupiter or Saturn. The overall spectrum of elements is about the same. It's just that there'll be different abundances because the temperatures of the sun are different than the temperature of the planets. Does that answer your question?
Yes. When the star dies, do the planets die?
Yeah, well, so that's a very good question. So it is thought that the sun and the planets and everything in the solar system are about the same age, 4.52 billion years. They formed about the same time. And in about 5 billion years, the sun will expand, become a red giant. It'll engulf some of the, probably Mercury and Venus will be inside the sun. We may be as well, the Earth that is. And the sun will then undergo additional evolutionary stages over the next several 100 million years. And eventually it will die out and become what's called a white dwarf, which is a very small, very hot, but very faint star. And at that point, what happens to the planets really depends on how much they rely on the sun for energy, because the sun will then be very different, very much fainter, and a lot lower source of energy than it is now.
Yeah, one more quick one I want to take.
Yeah.
So you believe the universe is shrinking? Is that how Mercury and the Earth will be in the sun, within the sun? Is the universe shrinking? That's it.
Well, okay. So we have to be careful with our nomenclature here, because I think what you mean is the solar system, not the universe. The solar system is composed of the sun and the planets, and the sun will expand after it use up all of its hydrogen fuel. It'll expand to engulf the inner planets, probably the Earth as well, but I'm not sure exactly. Definitely Mercury and Venus. But then it'll shrink back again and enter into a new phase of its evolutionary lifetime. But over time, it's going to get fainter and fainter and fainter. The solar system will become colder and colder. And so regardless of what happens to the Earth, in that first expansion, life on the Earth will be extinguished when the sun becomes a white dwarf, which is a much fainter and smaller, and a lower source of energy than it is today.
Thank you for your lecture. My question is the LIGO experiment, and the machines are now all over the United States and India and etc. Are they not giving you information on the black hole?
Well, they're giving us information about multiple things. So for those of you in the audience who may not know, LIGO is a network of gravitational wave detectors around the country that measure gravitational waves. Okay, well, what are gravitational waves? Well, it is thought that space, the space that pervades the universe, actually can be thought of as a sheet of fabric. And so gravitational sources in this sheet of fabric produce dimples or waves in the fabric. And so when a source of gravity, like a black hole, moves or collapses or expands or explodes or whatever, it causes waves in this fabric to emanate outwards. And so these gravitational waves emanate from the black hole event, and of course they emanate throughout the whole universe, or most of it, and we can detect them from very far away using this gravitational wave detector. And I think what you're asking, sir, is what can we learn about the black holes from these waves, right?
Right.
Okay. And so the primary answer to that is what we learn from these waves is what exactly happens when, say, a black hole and a neutron star collide, or two neutron stars collide and explode, or these interactions that involve very strong gravitational fields that exist in black holes and neutron stars that we can't necessarily study in any other way because they don't give off much light. We can study them using gravitational waves. They're dark and they don't give off light, which is a form of waves, but they do give off gravitational waves. And by studying the structure and how those waves, how how long it takes them to get to us and how they emanate and how they behave, we can study the exact details of how these black hole neutron star interactions occur, and hopefully use those to hone our models of how these things behave. Because as astronomers, we get 95% of our information from the universe by light, the light we receive from them. Light has a whole range of wavelengths. The light your eye sees is a very small fraction of the entire spectrum of light itself. We see visible light, but light also has longer wavelengths, the radio waves, shorter wavelengths, the X-rays and gamma rays. But if you don't have any light, like in a black hole, you have to find some other way to study it. And gravitational waves, which are obviously quite prominent in the life of a black hole, are the main way to study those kinds of phenomena.
Thank you. I have one other question. You don't have to answer. Sure. Do you think there's life out there somewhere in space?
Okay, thank you. Good question. So I would refer you to my podcast because I get that question all the time. And so I decided to just record a 2-minute piece about that. In fact, I get 2 questions, and I don't mean to, to belittle the audience, but there are 2 questions I'm always asked, which is, one is, do you believe in UFOs? And the other is, do you believe there's life elsewhere in the universe? And so I recorded 2 podcasts that answer those questions from my standpoint. Okay. But as far as life in the universe, the way I look at it is this. In a statistical way, there are a lot of stars in the galaxy, 100 billion stars. There are a lot of galaxies, millions, if not billions of galaxies. If we just think about the statistics and the percentage of stars with planets, there must be some other planet somewhere in this universe that has some kind of life, if not intelligent life. Now, how we would find out about them is a whole other question, because of course, the speed of light is as fast as we can communicate with them. So, and they're so far away, or they may be so far away that we can't actually communicate with them. But statistically speaking, I believe the answer is yes. There is life somewhere out there.
Thank you for your talk. From an physics point of view, can you explain form is emptiness and emptiness is form?
So I tried to, good question. I tried to steer clear of the philosophical aspects of the painting. As you notice, my talk is almost exclusively focused on the physics and the astrophysics. What that phrase means, emptiness is form and form is emptiness, is up to each of you of your individual interpretation. That's how I look at it. But in my case, my interpretation would be that when we look out into space and we see darkness, we think that's empty. In reality, it's not. Almost all of space is not empty. There is something out there. Form is out there. And even in what we would call a vacuum, there are particles floating in space. They tend to be hydrogen and dust particles. So I would say the form part are the particles that exist. The emptiness part are the appearance to us, which looks dark and with nothing. That's what I would say. Form is emptiness. Emptiness is form.
That's wonderful, and I think I'll chime in just a little bit there. The form is emptiness, emptiness is form. Passage, we study that a lot as, if you study it as a Buddhist from that perspective, we have to be really careful. It's emptiness, it's not nihilism, it's not nothingness. There's this fine line in between that we're always trying to reach. So thank you for elaborating on that.
Personal note, I retired from FAU.
Yes.
And I had lunch with Bjorn Lamborn almost every day. I was chair of chemistry, he was chair of physics, and I think he'd be very pleased with the person occupying the chair that has his name.
Thank you so much for the kind words. Yes, I did not know Bjorn, but of course, I knew he was chair of physics for a long time. He's passed on now, and his sister is alive. I know her very well. Her name is Ingrid Bordner, and we talk on a regular basis, and she speaks very highly of Bjorn and the time he spent at FAU. And of course, she speaks very highly of FAU itself, too.
I do have one question. Your question to us about if the sun suddenly became a black hole, what would happen to the Earth? And your answer was nothing. Yet you showed a picture of a black hole at the center of a galaxy covered with light from material falling into it. So I can't reconcile those two positions.
I see, right. Well, you have to remember that the sun is located in a part, in what I like to call the suburbs of the Milky Way. We're out in the middle of nowhere. There really is nothing. I mean, the nearest star is 4 light years away. And there isn't much gas or dust in our vicinity in the galaxy. Whereas in the center of the Milky Way, it's completely different. It's a lot more, it's more the, the downtown, if you will, of the galaxy, while we're out in the suburbs. So the center of the galaxy is a lot more going on. There's a lot more material, raw material for the black hole to ingest. Whereas where we're at, it's basically not much going on. Mm-hmm.
Thank you.
Sure.
Yes, and thank you all for coming today. How about one more round of applause for our good friend, the physicist? Thank you so much. You all have a wonderful day, and I encourage you all to please go into the exhibition and enjoy that beautiful painting in person.